Hi there everybody, welcome to another MCAT ACE lecture, and in today's lecture we're going to be working with general units and conversions. So this is one of the first things that students will learn in general chemistry when they come across one of their first chemistry courses. So before you start getting into the atoms and all of the other material in terms of actual chemistry and electrons and things like that, most people will go through a units and conversions chapter at the beginning of their course. And this is very important because it's going to carry through to any other chemistry field or process that you would be doing some sort of math in. You're usually going to find conversions, and you will certainly come across units where you need to understand the difference between Celsius and Kelvin or grams and moles and things of that nature. So this is a very basic unit, but it's a very important unit that you are comfortable with. Especially if you are taking the MCAT, you cannot be wasting excessive time trying to figure out conversions. You need a strong methodology as far as how you're going to set them up, execute them, and then move on to the next question in your limited time window. So you want to make sure that you've got this stuff down before you go on and you start mastering the content. So what are we going to talk about here today? Well, the first major topic that we need to bring up is significant figures. There tends to be a lot of confusion around significant figures even once students get out of general chemistry. So it's very often I'll find students that are writing organic chemistry lab reports, they're doing their limiting reactants or things like that, and significant figures have kind of gone out the window and people aren't focused on them as much anymore because you're on to bigger and better things, so to speak, when you're learning all these new reactions. However, it is very important that you understand and you observe significant figures when you are reporting any data or any scientific work that you are, whether it's publishing, reporting, and handing to somebody else you're working with. You need to keep track of that kind of stuff. And we'll talk about why, the meaning and why they're important. We'll certainly go over the rules as to what makes something a significant figure or not, and we'll have a brief discussion on accuracy versus precision, which is one of those common topics that always comes up in first semester chemistry. Then we'll take a brief look at scientific notation, which is the idea of taking either very large or very small numbers and shrinking them down into a more manageable written form, and then we use some sort of an exponential multiplier. So you usually see something times 10 to, and then it's a given power. So for example, 2 times 10 to the 7th. And that would represent taking that 2 value and then putting a bunch of zeros after it until you hit the millions value, the 10 millions there. So we'll take a look at that, going in both into scientific notation and out of it. What if I want to get out of scientific notation and actually write that very large or very small number? We will discuss common SI units, which are the standard international units, particularly the metric system. It's what everybody agrees upon as they're working with this in the scientific community. So especially for those that are viewing in the United States, we typically have the imperial system, and we're using things like gallons instead of liters. We use pounds instead of kilograms, and so you'll come across differences in that. And that's part of what we're going to head into with dimensional analysis afterwards, is how can I convert. Let's say somebody says, I've ordered 7.55 pounds of this compound. What would that be in grams? You need to be able to convert that and go back and forth, right? So that's the idea of dimensional analysis. You're going from one dimension or unit to another when you're converting back and forth. We'll take a look at some problems like that. And then with the SI units, we also want to talk about prefix values, right? So what is kilo or milli or micro or all these terms that come up, what do they mean? Because they're sort of modifiers that go on to base units, right? So for example, a base unit would be grams, and then you could have a kilogram, or you could have a microgram or a nanogram. We're still having the same base unit in each of those cases, the gram. However, that prefix is a modifier to tell us how much of that particular base unit, whether it's larger or smaller than the relative base unit that we would normally consider our standard unit. So at the end, we will definitely have our practice and summary as usual. But other than that, let's go ahead and get this underway and start talking about significant figures. So the first thing on the list here, the meaning of significant figures. I'm going to keep this somewhat short, but I just wanted to mention the importance, because a lot of students, other than feeling like it's just some sort of mathematical rule, they don't appreciate or understand why this is being implemented, and that's what I want to get across here. So significant figures, which I'm going to abbreviate throughout this lecture as SF, it just saves on the typing time for me. Significant figures represents the precision of your measurements and useful scientific information. All right, so what does that mean? It means that if I were to weigh, let's say, some sort of a toxic substance out on a scale, and the scale could read out to 2 decimal places. So it told me that I have 1 gram of this toxic substance, right? And I'm going to test this. Let's say it's on some sort of a lab test or animal trial test or something, right? So the scale tells me this, and then I turn around in my notebook and I write this. All right? So what's the problem with that? The problem is that I have given additional figures that my instrument did not tell me about. I'm making an assumption there as the scientific user and saying, hey, I'll go ahead and I'll extend this out 2 more values. All right? If this is as high as my instrument can go, the 1.00, it is not appropriate, and in fact it's considered dishonest for me to make up those 2 additional digits, because it could be anything as low as what I suggested, the 00, but what's to say that it wasn't this, right? Which at that point, if I'm dealing with a highly toxic substance, maybe that extra 10 milligrams of substance, which is getting close to pushing this over to this value right here, right? Maybe that extra 10 milligrams would make a huge difference in the results. And then I hand these values over to somebody, and they think that I'm being as precise and as accurate as possible when I'm giving them this information, and I'm really giving them a misrepresentation, right? So whether you mean to or not, you're lying about the precision of your measurements and how far out they can go. And that's not a good thing. You do not want to be doing this in the scientific community. In fact, in most colleges, it is considered a form of academic dishonesty if you're making up data. Now, most students, if they leave off or they add additional ones, they don't necessarily have the purpose or the intent of being academically dishonest, but a lot of teachers will strive that point home because it is very important once you do get out and you're publishing papers or you're keeping track of a scientific journal, whatever it might be, you need to have a accurate representation of what your instruments are producing in the lab. And you should not be either shaving numbers off, which is then you're sort of lying by omission because you're hiding things, or even worse, adding numbers on, because at that point you're making up data that didn't exist. All right, so that's the importance here. And you can see the note I have here, adding or omitting significant figures is considered dishonest, and it is very frowned upon in the scientific community. You do not want to be making up numbers, whether you intended to or not, by extending these values past what your instruments are telling you. So then a lot of students will ask, well, how do you get better or improved numbers if I'd like to report more? And as most things come in industry or medicine or anything like that, it comes down to money and to cost. So you can usually buy better instruments if you have more money to sink into them, and then they will give you better data, or at least data that has more numerical values to work with in return. So that's just something to keep in mind as you're discussing significant figures and thinking about them. So now let's talk about the rules of significant figures. This is going to be broken up into 2 parts. It's the rules of determining whether a value is significant or not. That's the first part. Then we'll talk about accuracy and precision briefly. And then the second set of rules are going to involve when I do calculations, how do I determine the number of significant figures that come out, right? So if I multiply a value that has 2 significant figures by 3 significant figures by 4 significant figures, does my answer have 2, 3, or 4? I need to know that as far as what I'm going to report back out, right? So maybe I had 3 different instruments that I was using, and I have to combine those values together. Maybe one of them was a mass and another one was a volume, and I used 2 different instruments, like a calibrated scale and a graduated cylinder, in order to find density. Well, if they don't have the same number of sig figs, which one do I report? So we'll be talking about that. All right, now, rules for significant figures. If you are going to attempt to just look at a number, so forget all the mathematics right now, you're just looking at a number, you should be able to determine the number of significant figures being reported to you as the user. So if I give you a number, even without a unit, you should be able to look at it and say, this is the number of significant figures that you are reporting to me based on this value. So let's take a look at the rules that make that up. There's about 6 of them total. Number 1, and the easiest rule, and you always reference the rules higher in the list to determine if you get into an area where you're not sure. So rule number 1, all non-zero digits are going to be significant figures. So that means 1 through 9 would be considered a significant figure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now when you get to 10, that's 2 units, right? 2 digits. A 1, which would be significant, and a 0, which we haven't talked about yet. Zeros are really the ones that are up for question, and all the other rules are going to help in terms of establishing whether I look at a 0 and it will be classified as significant or not. So 1 through 9, anytime you see them, you have a significant figure. Now, what happens if I have zeros between 2 non-zero digits? In that case, Rule 2 says that all of the 0 digits will be counted as significant figures if they are between 2 non-zero digits. So, for instance, if I have 505, because this 0 is in between the 2 5s, both of which are non-zero digits, this 0 would be counted as significant. And so I would say that there are a total of 3 significant figures when I look at that value. Now again, we haven't gotten to units yet, so it could be 505 grams, it could be 505 liters, whatever it might be. It doesn't matter at this point. All you need to be able to do this far, okay, is determine the number of significant figures that you're looking at. Now, leading zeros are never considered significant. That is rule number 3. So what do we mean by leading? We mean any zeros that come before your first non-zero digit. So let's say that I've got something like this, 505 right here. All right. So now the question is, what about all these other zeros? We know that this 0, because of rule 2, which is higher on the list, is significant. So that will be a significant figure when I'm working with it. When I take a look at all of these other zeros, these would not be significant because they are leading up to the first non-zero digit, which is the first 5 that we see there. All right, so all leading zeros will not be significant. Now, once you hit your first non-zero digit, so in this case it was 5, at that point the leading term gets cut off, and then anything else you need to apply the additional rules to. All right, so again, that's why that 0, even though that 0 between the 2 5s is leading that second 5, the last 5 in the number there, it's not considered a leading 0 because higher on the list is if a 0 is between 2 non-zero digits, and it fits that value there. All right, now, number 4, all trailing zeros are significant figures, provided a decimal is found. So what does this mean? This means if I take a value such as 5.00, right, these are trailing, okay, zeros. They're coming after the first significant non-zero digit. However, they're not between 2 non-zero digits. So I can't really apply rule 2 here. It's not like I have another 5, right? In which case then I could apply rule 2. It's just that the zeros continue after that. So if a decimal is present, 5.00, any of the zeros that are trailing a non-zero digit are going to be considered significant. So this would have 3 significant figures. Both of those zeros would be counted as significant in this case because there is a decimal and they trail a non-zero digit. Now, what happens if there's no decimal? Rule 5 handles that, and this one's a bit ambiguous as far as how we determine it. So with no decimal, 0 values are unknown regarding significant figures. So an example of this would be, what if I say I have 5,000 and I report a value this way? I don't put a decimal point there. All right. So what you could say here is that you are sure you absolutely have one significant figure. Okay, without a doubt. It could be, so maybe 2, it may be 3, or it may be 4. Now it shouldn't go above 4 because there's only 4 values here, right? However, without the decimal point, when it's reported that way, you are not sure. So it's kind of left up for the user to interpret, which means that in general, we try to avoid reporting numbers that way unless they are an exact number or an exact conversion, which is what we'll talk about in the next rule. All right, so what do I mean by an exact number? Let's say that you were counting people that were coming into a concert. If you count exactly 5,000 people, you can be sure that this number is 5,000, and you can call all of these significant at that point. All right. But if you just said it was measured, so it was measured to be 5,000 liters, right? Let's say that you were measuring some large body of water, and you said it was measured to be 5,000 liters. Well, if you're stating that you're measuring it, that means you have an instrument of some sort. And if that instrument does not give you decimal places, then you can't really be sure as to where the cutoff is here with your uncertainty. All right, so we try to avoid these, but if it comes up, you should realize that you are going to be stuck with a little bit of uncertainty there. Now, let me just show you one other value here. What happens if I were to report 5,050, right? So in this case, note that this 0 here is between the two 5s, and Rule 2 is in place before Rule 5 is in place. And so this would be considered a significant figure, that second digit there, the 0 in between the 5s. This one trails, there's no other non-zero digit after it, so this is a trailing one, all right, and there is no decimal point, so this one's questionable. So the minimum that you would have here would be 3 significant figures. You are sure of those first 3 numbers using the higher rules on the list. And then it could be 4 significant figures. We're not as sure about that one. All right, so number 6, all exact conversions or discrete countable objects have an unlimited number of significant figures. That was kind of like the example I gave when I said you're counting people. So if you have an example like that, all right, let's say, for instance, I own 2 dogs, okay? It is appropriate, if I were to report that I could just use the number 2, and it's not considered 1 significant figure, it's not considered 2, it's not considered 0, it's considered an infinite number of significant figures. Now, why is that the case? Because if I say I have 2 dogs, that's the same as saying I have 2.0 dogs, or 2.00 dogs, or 2.000 dogs, and I think you get the point. I could extend this out, right? Because I'm never going to have a millionth, or a trillionth, or a billionth of a dog. I'm always going to have exactly 2 dogs, right? Or you could say, I have 12 donuts. If you're talking about them and you can discretely count them, you know you have 12 donuts in the set, or 12 pencils, whatever it might be. That is a discrete countable object, okay? Now, if I have a line on a piece of paper, and I say, let me get a ruler, and I measure that line, and I say, oh, it looks like it's 3 inches. That is no longer considered a discrete countable object. I can't just list off and count the inches in the line without an instrument. And so when I bring the instrument into this, right, at that point I set up the need for significant figures. And I can't just say they run into infinity, because that ruler has limitations. Maybe it's millimeters, maybe it's smaller than that if you have a really good ruler. But it's going to run into a limit at some point where it can't continue to fraction all the way down to the smallest, infinity as you're going on. So this also applies to exact conversions. So what do we mean by exact conversions? For instance, if we say 1 inch is equal to 2.54 centimeters. All right, so this is not 3 significant figures if you're using this in an equation. That is an infinite number of significant figures. And that is because we are defining 1 inch as exactly 2.54 centimeters. So you could turn around, if somebody said, what is an inch in terms of centimeters, you could say 2.54, but you could also say 2.540, you could say 2.5400, right? And you could keep going on. There is no limit to how many zeros you can add on there. So whether it's yards and feet, or whether it's inches, centimeters, gallons, liters, if you have an exact conversion that states there's this many in this many, that's the definition of that unit, then you have an infinite number of significant figures, because you are defining it, and therefore there's no questionability as far as the units are concerned. All right? So those are the rules for significant figures. Now, obviously, when we get to our testing portion, we will be testing you on those, so make sure you're comfortable with that. All right, now let's briefly talk about accuracy and precision here. So accuracy is how close a set of measurements are to an accepted value in the community, usually a scientific community. All right, so if you want to say my results are accurate or my data is accurate, you need to have an accepted or a known value that is comparable. So let's say that you continuously in a physics lab, you're dropping a ball over and over and over again from a given height, and you're measuring the acceleration due to Earth. You have an accepted value of approximately 9.8 meters per second squared. So if you are getting that as your acceleration or very close to that when you're averaging the numbers out, you could say that your data is accurate because you have a known or an accepted value that has been established over a long period of time and is accepted by the community as a whole as the given value. You have a known to compare your values to. So accuracy cannot always be determined because let's say that you're pioneering or you're trying to figure out some brand new equation or unit or something like that in a field. If you don't have something to go off of, a known value, you are the one that is starting to establish that value. Now, once you've established it, it doesn't mean that it's accurate all of a sudden, it's the accepted value. You need others to repeat the experiment, right? We get into the whole scientific process at that point. But when we talk about accuracy, if there is a known value, an accepted value, you can look at that and say, how close is my data or my individual points I've collected and their average to that accepted value? Am I on track with what the community expects, right? Now, precision. Precision can, in theory, always be achieved with good scientific setup and instrumentation because you don't need a known value to achieve precision. Precision is how close a set of measurements are going to be to one another. So let's say that I'm going back to that measuring example for gravity and I say, oh, I measured at 5.4 and then I measured at 5.3 and then I measured at 5.4, right? I'm by no means accurate because I'm nowhere near the 9.8 meters per second squared if I'm taking these tests and I'm looking at the acceleration. However, you could make a case that I am being precise with my measurements because they're all falling relatively close to one another. I don't have a huge scatter of values or a huge range is the term we would use statistically. These numbers don't go all over the place. They're staying in a nice close-knit area as far as my precision is concerned. So you could say that that would be precise as far as the measurements, right? Now you could have your measurements all over the place and then you average them out and they come close to the known value and then you can claim some accuracy, but you've got a massive issue with your precision. So the idea here is that precision and accuracy, you want them to go hand in hand. You would ideally like to be precise and then you would also like to be accurate. You don't just want to have wild fluctuations and then say, well, they all average out, so who really cares? At that point, you've got serious variability and error with your instrumentation that you need to take care of before you would move on and start judging the accuracy. All right? So that takes care of accuracy and precision. So what I'm going to do here is clear the board off because I got a lot of writing up here. And then I will discuss, as far as mathematics are concerned, how we apply that to significant figures, and then that will lead into the discussion about scientific notation. So just give me a moment to clear the board here, and then we'll take a look at that. Okay, so let's pick up here with the rules for significant figures, and this is in relation to when we want to do some sort of a mathematical arithmetic transformation. So adding, subtracting, multiplying, dividing. When we're working with this, there are different rules for multiplication and division than there are for addition and subtraction. So for multiplication and division, which is probably the one you're going to run into more often in most of your questions, but you could certainly have addition and subtraction present too, you're going to deal with the smallest significant figure value, and that is what would be reflected in your answer. So that's how you're going to deal with multiplication and division. So for instance, if you have a set where there are 2 significant figures multiplied by something that has 3 significant figures multiplied by something that has 4 significant figures, Whatever that comes out to when you multiply it can only have two significant figures in the answer, because the lowest number of significant figures, or the smallest set, okay, is going to be reflected in the answer. So if I only have two significant figures for one of my values, that's the limitation. Now the reason for that is that if this is the best my instrument can provide at this point, that's the limiting factor. I'm getting more and more information each time here, but one part of this equation has a severely restrained number of significant figures. And so the answer itself inherently is going to have to show that limitation, even if the other data might be there for the other measurements. Because that one that had such levels of uncertainty made it into the equation, the answer has to reflect that. That's the only appropriate way to show that. So when you do addition and subtraction, it will be based on the decimal point. So let's say, let me give you an example here. All right? So let's say that I have 15.0, right? So that would be 3 sig figs. And then I have 2.50 that I'm going to need to add to that. And then let's do one with 4. 7.255, right? So I want to add all of these. Now, if you went through and you were to add all of these up, the answer that you should get would be 24.755. And that would be a good time to remind people we are going to be doing math in this lecture, so having a calculator handy would be a good idea. All right, so if we take a look at this, okay, the question is, where does the last place for all decimal values align? Now let me make this clear, so I'm going to switch the colors here to red just so that it's obvious. If we look, the last place that they all align is this place right here, the 10th place. Okay? So that top value, 15.0, does not go out to the 100th place, even though the others do. And the top two values, the 15.0 and the 2.50, do not go out to the 1000th place, like the 7.255 does. So those numbers are limited when we're adding up. We don't know, right, if it's a 0 here or if it's a 9 that might be there, or anything in between for that first value, the 15.0. We don't know if it's 15.00, 15.09, 15.03, etc. So we align it to the last position. This is where we have to cut the answer off. That's the way that you do addition and subtraction. So if I were to look at that, I have additional digits here, so I'm going to need to round. So I would say that the appropriate answer in this case would be 24 point, and then the 5 is going to round this value up. Remember, if it's 0 up through the value 4, you round down, and then if it's 5 up through the value 9, you bump it up and you round up. So if we're rounding up, it becomes 24.8 as the answer, and that would be the appropriate way to report back what you have here. Now your calculator is just going to usually spit out all of the potential digits. So you should see 24.755 in your calculator. You, as the scientific user, would need to understand how to weed out the digits that don't count and report only the proper digits back. Okay? Now, if, let's say I use this same set of values up here, I take 15.0 times 2.50 times 7.255, right? So if I multiply all these together, my answer will have 3 significant figures, but that's because I have 3 significant figures here, I have 3 significant figures here, and I have 4 significant figures there. So the lowest set of significant figures in this case would be 3 sig figs, and so my answer should report 3 sig figs. It doesn't have anything to do with where all the decimal places are aligning in this case. So if you went through and you multiplied all of these, your calculator would spit back out at you 272.0625. Now that's too many sig figs, right? I've got a total of 7 there. The 272.0625 needs to be brought down to 3 significant figures max. And in that case, 272, if this is a 0, then this gets rounded down, so we just keep it where it is. And 272 is the appropriate answer. All right, now you could put a decimal point. You cannot put a 0 after the decimal point, but you can put a decimal point there if you want. Or you don't have to put a decimal point there because there are no ambiguous zeros here, right? 272, if I don't have that there, is 272. It's all non-zero digits. It's very evident that I'm talking about 3 significant figures in that case. So that's not a problem. Now, if we have a mixture, you need to follow the order of operations. So let's say that we have something in parentheses. You need to execute that first. If you have multiplication and you have addition, you need to execute the multiplication first and then do the addition. So you would do your multiplication, apply the rules to the answer you get out of that multiplication, meaning lowest number of sig figs present, and then take that value, add the other value to it, and then use the decimal point rule when you're adding in order to determine the final answer when you're looking through that. So you need to run through the order of operations if they're present in a mixed set like that. All right, and you probably have some sort of mnemonic for that, like please excuse my dear Aunt Sally. I've heard other ones, but you need to know it's parentheses first, then you're talking about your exponential stuff, right, which is really multiplication of a set over and over. Then you have multiplication, division, and then addition and subtraction. The biggest thing to remember is parentheses. Anything in those go first. Then you deal with your multiplication, division. Then you deal with your addition and subtraction. That's the order of operations when you're dealing with mathematics. So the next thing I want to bring up is a situation where we are going to run into a problem, and then that's going to lead into talking about scientific notation. So in another example that I have here, let's take a look at something where we would say, what was my example here? 15.0, so kind of similar to before, times, and then the value that we're going to multiply by would be 1000.0. So the answer here is 15,000, right? Now, if you take a look, this was multiplication, 3 sig figs and 5 sig figs. So answer should have 3 sig figs. And when I'm looking at this, I have to make a cutoff somewhere. 15,000 is not going to be able to be represented very easily as far as sig figs are concerned. So let's take a look at what I could do. Well, if I wanted to, I could say 3 sig figs starting at the beginning, 1, 2, 3. Well, 15 is not an accurate representation of 15,000. So I could say, all right, how about 1, 2, 3? Well, 150 is not an accurate representation of 15,000. I could say 1, 2, 3. Again, 1.50 is not an accurate representation of 15,000. And if you want to drive this point home, think that you currently are owed by the bank $15,000 in your bank account, and they can only have 3 significant figures in their software and their banking system. And so you go after making that deposit and you check your balance and they say you've got 150. And you say, no, I have 15,000. And they say, well, those extra zeros, we don't really know if they're significant or not. So we're going to call it at 150, and that's the best that our software can do, right? There would be serious problems with that. You would not be happy. So we have to have a way in science or math of taking these values that start to get very large and then for some reason need to be brought down or shrunk into an appropriate representation. So that is where scientific notation comes in. So what you would do for scientific notation is you're going to pick out a number between 1 and 10 because we're going to use a multiplier of 10 to condense this as a placeholder. So it can be anywhere from 1 up through 9.99, but once you hit 10, you should bring it back to 1, and that extra 0 will be subsumed into the placeholder. All right. So when you're working with this, if you wanted to make 15,000 appear with 3 significant figures, you would say 1.50 times 10, and now you have to figure out what multiplier or exponent you want to put up there. So keep in mind, every time you do this, you're going to exponentially raise by 10. So if I put to the second, that would be 100. So 100 times 1.50 would be 150. So that's not enough. I need to keep going up. And then to the third, that would be 1,000. So 1.50 times 1,000 would be 1,500. It's still not enough. I need 10 to the 4th. All right, so 10 to the 4th, if I look at that, would be 10,000. So keep in mind with exponents, right? It's 10, and then 100, and then 1,000, and then 10,000. So if you look at this, this is, right, 10 to the 1, to the 2, because it's 10 times 10, 10 to the 3, 10 to the 4, and we're going on and on like that, right? So 10 to the 6 is a million, 10 to the 9 is a billion, we keep counting up. So 10 to the 4 times 1.50 would equal 15,000. So this is an appropriate way to represent a large number with only 3 sig figs. I have 3 sig figs here, and this does not count as sig figs. This is just a multiplier, or it's often referred to as a placeholder. Okay, so it's saying, I will hold these extra values that you cannot hold on to, and I will tuck them into this exponential factor so that you can return them and you can get approximately, it may not be exactly, especially if these aren't zeros, you're going to lose some info. Let's say that was 1, 1 or something like that. But you will at least ballpark approximately get back what you were looking at, right? So that is going to be used in the case of very large numbers or very small numbers when you have to crunch in for the sake of space or the sake of reporting significant figures. You have to crunch in and report a smaller value than what you would normally write down, right? So this can be used for large or small numbers, and we'll take a look at an example of each. So if we were going to deal with a very large number, let's just rattle off some non-zero digits here. So 1, 2, 3, 4, right? 5, 6, 7. We stop there. A million something is large enough. Okay, 0.0. So if I take a look at this, I've got 1, 2, 3, 4, 5, 6, 7, 8 significant figures. And let's say for some reason I needed to convert this down into 3 significant figures. So the same argument as above applies. I can't turn around and look at this and say, well, we'll just call it 123 and that's about good. Because that's 123 doesn't come anywhere close to approximating 1,234,567. So what I would need to do is convert this into scientific notation with the appropriate multiplier. Now, some students like to count decimal points. Some students are comfortable with the exponential factors in their head. The easiest way to realize you've gone into a new unit is by threes. So 10 to the 3rd is 1,000. 10 to the 6th, right, because I'm adding an additional 3 zeros there, is going to be 1 million. And then 10 to the 9th is going to be 1 billion. And then 10 to the 12th would be 1 trillion, and so on and so forth as I'm going through that. So if you were to look at that, you can usually, if you know your 3, 6, 9, 12 stop-off points, then you know anything in between there would be 10 million, 100 million, then you hit a billion. 10 billion, 100 billion, then you hit a trillion, and so on and so forth. So if I wanted to convert this to 3 significant figures, okay, keep in mind I have a value of a million here. So a million would utilize 10 to the 6th. So if I do 10 to the 6th, I would say 1.2, and it's a 3, because if this is a 4, I would round down, so I keep the 3. 1.23 times 10 to the 6th. And if I took 1.23 times a million, I would then end up with 1,230,000. Okay, so I would lose this data in here, right, if I were converting back out. If this was all you were reported, you wouldn't know that this is what you had here. However, it's at least a much better representation to say 1,230,000 than to say 123. You're getting much closer to the value that you were initially reporting. All right, so that's how you would convert into scientific notation. Many students like to count the decimal. You can go 1, 2, 3, 4, 5, 6, and then place it between the 1 and the 2. I have no issue with that if that's what my students like to do. But again, keeping in mind and in the reference of, you're headed in to take the MCAT. Counting decimal points, if you don't know the numbers in your head, can be time consuming. It is also very prone to error because you can easily skip one, or you think that you counted one and you missed one. you need to be careful if you're going to count your decimal points. If that's what's easiest for you, you've already got too much memorizing in your head, use it as a tactic, but get good at it, and you need to make sure that you are doing it at a rapid enough pace with proper accuracy that you're not losing points on your test. All right, so then let's say that I have something if I want to convert out. Okay, so let's say I have 1.50 times 10, and let's make it a small number, to the -6. So I'd like to convert out of my scientific notation here. So again, you can apply the same multipliers or rules here, okay, or you can count decimal points if you would like to, just to double check yourself. So I'm not capping this at a certain number of sig figs because I've already been given 3, so I'm only going to observe 3 in my answer. But the question here is, how can I convert this out of that? Well, if this is your unit here, and here's the decimal, you know it's headed this way, you simply need to add 1 fewer zeros than the value that you have in your exponent. So in other words, if I have a -6 there, okay, so 6 if we're looking at the absolute value, I need 5 zeros in front of that 1. Now don't include the 1's unit 0, okay, but you would go 1, 2, 3, 4, 5, so there's my 5 zeros, and then it would be 1, 5, 0. Alright, so if you wanted to double check yourself that you moved 6 spaces over, you could go 1, 2, 3, 4, 5, 6. There's my 1.5. It matches back up. Right, so again, I would encourage you to get used to some common exponents in your head and utilize them, because they're going to come up fairly often, especially with unit conversion, which is where we're headed next. You want to be able to go into and out of scientific notation pretty readily when it comes to this sort of stuff. So with that, I'm going to clear up the board from the scientific notation talk, and we will start discussing common units and common prefixes, and then we'll meld all of that together into some dimensional analysis problems. So give me a second to clear the board, and then we will take a look at common units. Okay, everybody, so what I've brought up here are some of the most common standard international units that you come across when you're using scientific terminology. So let's go through these. Most of these should be familiar to you at this point. You should have seen these units used often enough during your undergraduate curriculum, but we are going to recap a couple of them here. So for length, we would have meter. For mass, we would have gram, and I just want to mention for mass, some people debate whether it's gram or kilogram. Gram is the base unit, although many times mass is shown as kilogram as being the accepted standard unit, especially if you're talking about in medical terms, because if we're weighing people or we're taking the mass of individuals, we would refer to it in kilograms, because that's the more standard unit that would be reported than grams. Grams would be a very large number for that. Volume is liter. Time is one that is universal throughout all systems. So second, right, here in the Americas we would use second, and then you would also use second in any other part of the world if you were talking about time. And then we can do minutes, hours, etc. Current, so we're talking about electrical current. You would be dealing with amps or ampere. Temperature, a lot of students confuse this one. They think that it's Celsius as the standard temperature. Now Celsius or centigrade is used quite often, but Kelvin is the official temperature that is recognized as the common unit for temperature. One of the reasons for that is that Kelvin is on an absolute scale. So that means that when you hit 0 Kelvin, that is the absolute zero temperature that you can reach. You cannot go below that. Whereas with Celsius and Fahrenheit, you can have negative temperatures. So there is such a thing as, for instance, -10 degrees Celsius or -200 degrees Celsius. It's not a perfectly zeroed out scale when you're working with that. Amount of substance. This is one that's common, and you'll find this in some of the other lectures that we have, and that is mole. So when we're talking about amount of substance, it could be anything from amount of water molecules or amount of hydrogen atoms or anything of that nature. A mole is going to be used to represent the actual number of particles, atoms, molecules, what have you, in a given sample. So again, some students start to confuse mass and moles when they're talking about this. So the best example I can give is if you imagine that I take 2 people, that is similar to the idea of moles. I have 2 individual people. Now the mass of those people could be different. So I could have two individuals that each weigh 100 kilograms, right? Or I could have two individuals that weigh 150 kilograms. The mass is going to be different in each case when you're looking at that. However, when you come to the number of people in both of those cases, it's 2. And so that's similar to moles. You could also compare it to something like a dozen. So if I say I have a dozen, depends on what I'm talking about, but you know that I always have 12 of that given unit. So a dozen bowling balls, considered in comparison to a dozen marbles, those would be two different masses if I were to actually put them on a scale and weigh the masses. However, the number of bowling balls and the number of marbles is the same. All right, so the amount of substance is related to mole. And then energy, we're going to talk about joules. Some people also talk about calories when you refer to energy, especially when we get into food, and food deals with kilocalories as far as energy is concerned. But joule is the common unit for energy. So let's talk briefly about the prefix multipliers, because a lot of students will get confused with these. So these are not all of them. There are some more extreme ones, like for instance, when you talk about femto, or you could talk about tera. So a lot of times when people talk about computer technology, right, you can talk about terabytes, which are larger than gigabytes. So you can see here that we do have giga listed, and giga would be 10 to the 9th. Mega would be 10 to the 6th, so that's a million multiplier. And then one of the more common ones, the kilo, is going to be 10 to the 3rd, so that would be 1,000. Then you have your base unit. So, for instance, if I have gram, right, then a kilogram would be 1,000 grams, a megagram would be 1,000,000 grams, and so on and so forth. So these prefixes are multipliers to the base unit. And then you get below the base unit as far as the multipliers are concerned. And so these are going to start being divisors. They're going to start making it smaller. So deci would be 10 to the minus 1. Centi, most people know centimeter, to the minus 2. Milli to the minus 3. Milli is probably the most common one out of the bunch down here. Micro would be 10 to the minus 6. Nano would be 10 to the minus 9. And the pico would be 10 to the minus 12th. So you can utilize these prefixes when you are attempting to describe a certain unit, whether it's a very large unit or a very small unit. So instead of saying 10 to the minus 9th seconds, you might just say 1 nanosecond, because that is representative of 1 to the 1 times 10 to the minus 9th seconds is what that would represent. All right, so these are the prefix multipliers that would go along with that. Now, these are important. You're going to want to know these, because when we move to the next part, dealing with conversions, we are going to have to be able to utilize these back and forth. And I will show you in the context of that in just a second here when we get started with those problems. So let me bring those up and we will practice some. Alright, so I brought a couple of practice problems up here, and I want us to go through these before we head into the practice session where you're going to be answering the multiple choice questions. Now, one other thing I just wanted to mention. Keep in mind that this is a very basic unit. So when I'm saying that, I'm saying this is review just so that you're comfortable with this stuff. But most of the questions that appear on the MCAT are likely going to be slightly more complicated than what you have here. But you're going to need to utilize these skills in the context of the heavier math questions that might appear on the MCAT. So just keep that in mind when you are working with things like this. This is practice to build you up to that. So when we are starting here, it says convert 0.0833 pounds to milligrams given, or that you know, 1 pound is equal to 453.6 grams. That's the conversion there. So I need to set this up. Now what I usually like to do when I teach this to my students is I tell them to set up what's called a canceling table. So you're going to start with what you know, which is 0.0833, and you'll put that in the upper left-hand corner of this divider table right here. And then you'll continue to fill in as you go along. And I actually, now that I'm thinking of it, I need to leave enough room here because we're going to work with units. So let's put pound. so we can keep track of our units. Okay, so that's what we're starting with right there, pounds. Now, in the bottom right corner of this next section of the table, you want to attempt to cancel out whatever you're not looking for. So if I want to get over to milligrams eventually, I have to get out of pounds. Now, I don't have a direct conversion from pounds into milligrams, but I can directly convert pounds to grams using the conversion that was given. So what I can do is I can say, let's get pounds down here. I put the unit down here first to make sure that they cancel one another, because that's what I want to get rid of. And I have to divide the units in order for them to cancel. So my conversion is that 1 pound is going to yield 453.6 grams when I'm doing this conversion. So now I'm in grams. The next thing here is milligrams. So I need my multiplier on the grams in order to convert this into milligrams. Now, some students they'll get confused here. So they know that milli has to do with 10 to the minus third. They don't know if it's 10 to the minus third up top or if it's 10 to the minus third on the bottom. The way I always teach students so they cannot make a mistake is that you take the larger unit and you're going to assign the 1 to that unit, meaning the number 1. So think about what you've got. You've got a gram and you've got a milligram up here. So the question is, which one is larger, a gram or a milligram? A gram is the larger unit. So 1 gram is going to be 10 to the third milligrams, right? Now, with 10 to the minus 3 over here, keep in mind that what this is saying is that 1 milligram is going to be 10 to the minus 3 grams. If you take a look at this, 1 over 10 to the minus 3 is the same thing as the 10 to the minus 3, right? So if I'm looking at these and I'm flipping them back and forth, you can utilize 10 to the third as long as you put it up in the numerator in this case. So if that sort of confuses you, that's fine. If you know exactly where you want to multiply times 10 to the minus 3, then by all means go ahead and do that. But I find that many students trip up going back and forth when they're trying to do that. So I always just say, put a 1 with the larger number, and then you need a bigger number, a larger number up here to make up the smaller units, because there should be a lot of smaller units in one large unit. All right, so if you have all of this and you execute the equation, you should return a number. And keep in mind significant figures here. If we're multiplying, some of these are exact conversions. We started with 3 sig figs, so we should end with 3 significant figures. And so the answer here should be 3.78 times 10 to the 4th milligrams if you calculated that correctly. So that is how you would go about doing that conversion. Let's take a look at the next one. Convert 275 liters to meters cubed, given that 1 milliliter equals 1 centimeter cubed. So they tell us our known value, and there is a given equation here, or a given equality. So we start with what's known. We know that we're going to have 275 liters that we start with. Now, I know I'm going to want to get rid of liters, right? And I'm trying to convert this into meters cubed. But I'm not going to have a direct conversion for that right away, so I need to think about where I'm going with this. So let's think about it. If 1 milliliter equals 1 centimeter cubed, then 1 liter needs to equal what? You should come up with 1,000 centimeters cubed, right? Because a liter would be a milliliter. Yes, a liter would be 1,000 milliliters. Had to make sure I was saying that right. So 1 liter would be 1,000 milliliters, and then that would mean that if 1 milliliter is equal to a centimeter cubed, 1 liter is equal to 1,000 centimeters cubed. So what I can do is I can say that 1 liter is going to equal 1,000 centimeters cubed. So I can start with that. Now the next part of this, if I want to get out of centimeters cubed, I want to get into meters cubed, I have to think about where I would go about approaching this. So let's think of the conversion of centimeter to meter. So I want to get rid of centimeter, okay, and we're going to have to cube this in order for it to cancel with what we have up here on the left. And I would like to bring it into meter. And again, I'm going to want to cube everything I have here because I'm looking for meters cubed as the answer. That's what I'm going after here. So if I plug this in, I'm going to end up that 1 meter, which is the larger unit, gives me 10 to the 2 centimeters. So 100 centimeters should be in 1 meter. Now remember, I need to cube everything that I have here in order to get meters cubed and in order to get centimeters cubed. So what's going to happen is that when I multiply this 3 times the 2 exponent on the centimeter, it's going to end up as 10 to the 6 for the centimeters cubed unit. So keep in mind that this is really going to be 10 to the 6 when I attempt to execute the equation here. All right, now if you look at the difference, I have a centimeter cubed on the top and I have 10 to the 6 on the bottom, right? So 1,000, 10 to the 3rd, divided by 10 to the 6. So if you do that, you're going to find that it would be 10 to the minus 3rd overall. So run this through a calculator. I'm going to bring this down here. And the answer that you should get would be 0.275 meters cubed. So that would be the equivalent to 275 liters. I would have 0.275 meters cubed when I'm working with that. Now let's take a look at this next one. A faucet has a flow of 1.70 gallons per 1 minute. So it's gallons per minute is the ranking on this. What is this in liters per second if 1 gallon is equal to 3.785 liters? So that's the conversion or the equality that we have. And we do have a starting point, and that starting point is the 1.70 gallons per 1 minute. So notice that at this point, we are dealing with a unit that has a numerator and a denominator as far as the final value, because we're looking for liters per second, not just liters or meters cubed or anything like that. So we would start with what we know, 1.70 liters, okay, and that is going to be per 1 minute. So 1 minute goes under here. That's what goes into the canceling table. Okay, now in the past, we haven't had anything other than an implied 1 at that bottom right-hand side. And that's because we were only dealing with a single unit. It didn't have a unit in the denominator. Now, as I continue forward, I need to tackle both minute and liter. So I have to pick out which one I want to do at the beginning. So what I can start with is I can start with the, this is gallons. Gallon. Jumped ahead of myself here. So liters, okay, see, this is why you want to set this up, because you can catch yourself. Gallon. So when you go over to liters, we have the conversion here. 1 gallon is going to become 3.785 liters. Now the gallons have canceled, so whatever my volume is now going to be in liters. And then I would also want to make sure that I convert my minutes into seconds. So if minute is on the bottom over here, it'll need to be in the top in order to be canceled out. Okay, so if it's minute and then I have second here, you want to say the larger unit is a minute. So 1 minute contains how many seconds? 60. Right? So once you have that set up, if you look at everything that crosses out here, you're going to end up with liters per second. So all that's left is to run the math, and when you do that, you should come out with the following. 0.107, and keep in mind 3 sig figs to begin with, so that's 3 to end, and that would be in liters per second. And this makes sense. This number got smaller on a per second basis. So this was originally in 1 minute, all right, and now we're talking about in a second. So we wouldn't expect nearly as much water to be delivered in a second. And we're also making the argument this is liters now instead of gallons, but it should still be much less in 1 second that's coming through that faucet. So that is how we deal with conversions and setting them up. So what I'm going to do now is bring up a couple of the multiple choice questions. Again, some of these might be a little bit more simplistic because this is a beginner's lesson when we're talking about unit conversion, but it's very important you master these skills in order to be able to properly perform on the more complicated problems. So let me bring up the multiple choice questions. We'll go over those and then we'll bring up a summary on units. Okay, so here are the problems that we are going to practice. So number one, how many milligrams are in a kilogram? So there's a couple of different options here. This is really testing you to make sure that you're comfortable and okay with your prefix multipliers. So you need to be able to go from milligrams into kilograms. A milligram is a smaller unit, so we would expect a large number of them to make up a kilogram. And you can see your options here are relatively large numbers. Number two, a given medicine bag is stated to have a concentration of 5.50 grams per liter. What is this in micrograms per milliliter? And you have several options there. So this is going to be dimensional analysis, unit conversion, like those problems that we just practiced a minute ago. Number three, how many significant figures are in the following measurement? So you take a look at this measurement, probably came from a scale given that it's grams, and you need to determine the number of significant figures that should be reported based on this number. Is it 9, 7, 5, or 4? And then finally, for number 4, a jogger runs 1.00 miles in 13 minutes. What is this value in meters per hour if 1 mile is equal to 1,609 meters? So those are the 4 questions we're going to use to practice here. And just a note for the second question where it says microgram, you'll see that I have used the letter U here. Sorry about that. I've used the letter U here. Now when we get ready to talk about a microgram, it is the Greek letter mu, like this. So when you see the U here, I do not have the ability to make this symbol on the program, but as you see me writing it out, it's going to have this extra tail over here. And that's just the proper way to represent micro when you're writing. So go ahead and attempt to answer these questions, pause the video, and then you can unpause it for your walkthrough. Alright, so hopefully everybody had a chance to work on this. So let's switch over to the red ink here and go through our problem solving. So how many milligrams are in a kilogram? You can set up a whole bunch of math for this, or you can just do some quick analysis. And since the goal on MCAT is to try to certainly answer the questions correctly, but to do it in the limited time frame that you have, so you have some time for the more difficult questions, you want to be comfortable with these multipliers. So if you think a milligram over to the base unit of grams is a multiplier of 10 to the third, and then a gram over to a kilogram is another multiplier of 10 to the third. So if you're looking at that, milligram 10 to the third, then gram to kilogram 10 to the third, you combine those to get 10 to the 6, and 10 to the 6 is a million. So the rest of these options are out, and at 1 million is the correct answer. There would be 1 million milligrams in a kilogram. All right, number 2. A given medicine bag is stated to have a concentration of 5.50 grams per liter. What is this in micrograms per milliliter? So we've got 2 units we're going to need to convert here. Let's start with what we know. 5.50 grams of the medicine in 1 liter of the medicine bag. So we get ready to convert this. We can do either liters or grams first. I'm going to go ahead and do grams. So let's get rid of grams. 1 gram, those units cancel. The microgram is a smaller unit. There is 10 to the 6 micrograms in 1 gram. Then, once I have micrograms in my numerator, the denominator, which has liters, needs to be changed to milliliters. So 1 liter, the liters can now cancel out, is going to go to 10 to the third milliliters. And so if you run through the math on all of this, all right, you should also see that the 10 to the 6th divided by 10 to the third, that is going to give me a 10 to the third when I work with this. So if you ran this through your calculator, you would indeed find that it's 5.50 times 10 to the third micrograms per milliliter if you're observing your significant figures. And so it is about approximately 5,500 micrograms per milliliter. So D would be the correct option here of the bunch. Number 3, how many significant figures are in the following measurement? You should have been able to answer this very quickly, provided you know the rules. So the first 2 zeros are leading. Leading zeros are never considered significant, so they drop. The 3 and the 2 are non-zero digits. Any non-zero digit are significant, and so the 4 and the 5 would also be counted. This 0 in the middle here is between 2 non-zero digits, so that also counts. And then trailing zeros will count if there's a decimal point, and in this question there is a decimal point associated with this measurement. So you tally those up, you've got 1, 2, 3, 4, 5, 6, 7. So 7 significant figures. Answer B would be the correct one. 4. A jogger runs 1 mile in 13 minutes. What is this value in meters per hour if 1 mile is 1,609 meters? So let's get ready to set this one up. We would say that 1.00 miles, which I'll abbreviate with MI, is going to be accomplished by the runner in 13.0 minutes. So initial values, we have 3 sig figs. So the answer should have 3 sig figs, which you can note all of the answers over here do. Now, as I get ready to convert, the exact conversion for meters into miles is 1,609 meters per 1 mile. So a mile is the larger unit, it gets the 1, we cancel that out. Now, the next thing I need to deal with is the minutes, and I'm looking to convert those into hours. So minute can go up top in order to cancel out the minute on the bottom, and there are 60 minutes in 1 hour because hour is the larger unit. So if you solve all of that, you'll end up with meters per hour. So multiply that together, and you should find that your answer comes out to 7.43 times 10 to the third meters per hour. And so answer B is the correct selection here. Okay, so hopefully everybody was able to follow along with these different manipulations of the units and the equations that we were setting up. And you should also have a good feel for your significant figures when you come across them. All right, so what I will do now is clear the board here. I will bring up the summary, and we will go ahead and get ready to wrap this lecture up. So give me just a moment, and I'll bring the summary up. All right, everyone, let's wrap up here with a summary of everything we've discussed in this lesson, and then we will complete the lesson on general units and conversions. So we started with significant figures. We talked about the importance of significant figures and why they actually matter. So as far as scientific honesty, when people are reporting numbers, in the science community and the medical community, when you're looking at peer-reviewed studies, you need to be able to take data, and if you would like to rerun an experiment or set up the same conditions, it is very important that you know exactly how precise individuals were with their data collection. And so making up digits or leaving digits out that were not accounted for by your measuring instruments is not appropriate. So remember, your significant figures are going to be limited by your measuring device. So the better the device is, which usually means the more expensive the device is, the better you will get as far as the number of significant figures that you can utilize. Now, what are the rules for determining if a value is considered a significant figure? So number 1, we said all non-zero digits 1 through 9 are significant. Number 2, any 0 that is found between 2 non-zero digits would be significant. So for instance, 101, that 0 in the middle would be considered significant. All leading zeros are not going to be significant. So if we have, for instance, 0.00025, all of the leading zeros up to that 2 value would not be considered significant. They are just a placeholder. All trailing zeros that have a decimal point present in the value are going to be significant. And then if there's no decimal point, the zeros become uncertain. So we usually try to avoid that situation as often as possible. but we cannot be sure if a decimal point has not been reported. And then finally, rule number 6, if you have an exact conversion, for instance 2.54 centimeters in 1 inch, or you have counted objects, so we've used examples like a dozen donuts, you can count all the donuts, or I mentioned I have 2 dogs. If they are objects that can be discretely counted individually, then you have an infinite number of significant figures. So if I said I have 2 dogs, I have 2.000 into infinity. There's no tenth of a dog or anything like that. So those would be infinite. And we do not consider them in calculations. If you do a conversion and you have an exact conversion sort of mixed up in your calculation, or it's sitting in there, you don't consider it when you're doing significant figures, because it would have an infinite number of significant figures, and you don't want to take your answer out to an infinite number of places. We then talked about accuracy versus precision. This is the common lecture that everybody gets in general chemistry. Remember that accuracy is if you have a known value, how close do your values come to that known value, or an average of your values. Precision, in theory, is always possible. So you may not be able to be accurate if you don't know the known value that you're shooting for, especially if you're pioneering in a certain field. However, you should know if your data is precise. Is it always hitting the same mark over and over again when you have a collection of it, statistically speaking? We talked about scientific notation briefly. You want to be comfortable going into and out of scientific notation. This is for very large or very small numbers typically. It can also be utilized when you have to limit your number of significant figures and you have a large number. So for instance, if you had a number like 5 million, but you could only represent it with 2 significant figures, you could make it 5.0 times 10 to the 6, and you get away with only 2 sig figs. However, you still accomplish the expression of 5 million instead of just 5 by using the scientific notation. Remember, the key or the trick that I gave you to work with here is that you want to be familiar with exponents of 3 in order to get quick results. So 10 to the 3rd is 1,000, 10 to the 6th is 1,000,000, 10 to the 9th is 1,000,000,000. If you know those markers or those part waypoints, you could really figure out anything. So if you turn around and then you say, so what is 10 to the 5th? Well, you think 10 to the 6th is 1,000,000 and 10 to the 3rd is 1,000. So the 5th would be 2 ranks up from that. That would be 100,000. So if you can keep that in mind in your head, you should be able to have a jumping off point for each of those, especially as they get larger and larger, like 10 to the 11th or something like that. Now, for SI units, the main units we discussed were meter, gram, liter, second, ampere or amps, Kelvin, mole, and joule. So those are the standard units that you're going to come across. There are certainly other ones like Celsius or calorie. However, when we are working with the base unit that is accepted all over, those are the ones that we go off of. Now, many of these units can have prefix multipliers, which we were discussing. So you need to know the ones that I put on the list here by memory. There was a good handful of them. But more than any of them, I'm pointing this out here, you need to be comfortable with kilo, centi, milli, and micro. Those should be a priority. I would also argue that nano kind of creeps in there. Nano can be used very often. But especially if you're going into medical fields, you're trying to work with MCAT and things of that nature, micro, milli, centi, and kilo are all going to be very important when you're dealing with masses, whether it's doses of drugs or weighing individual human beings. Those are all very important multipliers. Okay, and then finally we talked about dimensional analysis. So this is being able to take a set of units and turn them into another set of units, provided you have the proper conversion factors. So miles to meters, gallons to liters, things of that nature. So remember, I suggest setting up a canceling table so that you can keep track of all of your values. Some students are comfortable with fractions, so you just multiply your fractions out. It's the same thing as a canceling table. It's a little less structured, but most people are okay with that. You use whatever works for you. Also, keep in mind that if you struggle with where to put the negative exponents when you're dealing with some of these multipliers, you can always keep the larger unit as 1, and then the smaller unit should get the larger multiplier or the larger number, so like 10 to the 3rd, 10 to the 6th, etc. And that pretty much covers it from start to finish as far as what we talked about. So that is going to be it for the General Units and Conversions chapter. And this has been a presentation by MCAT ACE, and we hope to see you guys for future lectures. Thanks for learning with us.